So this morning we see classical theory, kinetic equation, then modeling, and now we have Lorenzo Pareschi speaking about numerical methods essentially for kinetic equation, particularly application in uncertainty quantification. So thank you.
Thank you, Giacomo. So first I would like to thank Alessia, Sara, Mattia, and Giacomo for the kind invitation and for the opportunity to give some lectures on a topic I've been interested in the last couple of years, which is uncertainty quantification. In particular, I will focus here the notion of UQ, as it's usually referred, uncertainty quantification, to the particular case of kinetic equation. So, since this is a course, I will cover some introductory material on uncertainty quantification for general partial differential equation. I would say this is somehow the main topic of my lecture of today. Of course, I'm not aiming at giving 1 hour a general course on uncertainty quantification, but I'm going to try to focus on what I think are the main aspects which are relevant in the case of kinetic equation, in view of application to kinetic equations. After that, essentially, I will focus on kinetic equation, and the remaining 2 lectures are essentially focused on how to obtain state-of-the-art uncertainty quantification techniques which are being specifically designed for kinetic equation. So essentially 2 and 3 are closely connected. We will see how to improve stochastic techniques based on Monte Carlo methods for uncertainty quantification, and I will start with the most simple and basic scenario, and then we'll then follow a bottom-top approach by increasing the complexity of the model and of the methods in order to introduce you the situation where essentially I use multiple model to improve the statistical properties of my equation. This I will arrive up to the classical multi-level Monte Carlo method in this topic. Then, if time permits, hopefully yes, I'm gonna speak about a different kind of approach, which is based on somehow on the use of orthogonal polynomial in the random space, and I will show you essentially how to derive method which have some interesting feature in the case of kinetic equation. Anyway, all these methods, so the kind of method I'm going to use in 2, 3, and 4 will be all introduced today in their general setting. So don't be afraid if you don't have understood a single word of 2, 3, and 4. Okay? As it's usually in numerical method, there are many techniques, so you have a lot of different acronyms which makes things somehow confusing. So let's focus on the general situation of uncertainty quantification for partial differential equations. So the typical situation is that in many cases where you develop a mathematical model for some kind of application in physics, biology, socioeconomy, as we have seen in the last lecture of Giuseppe, financial, then this kind of system, they always involve uncertainties. Namely, we design partial differential equation, we design model, and all these models are derived by assuming that the quantities that we are dealing with are deterministic. Okay? But of course this is not the case, especially if you move away from classical physics, so you don't even have first principles, and you at most can hope to have some statistical information on these parameters. We shouldn't even push too much this idea in general, because typically what you really have is a lower bound or an upper bound of a certain quantity, and then you take things uniformly distributed about these two extrema, or you have some mean of a certain quantity, some variance, and then you take these kind of quantities distributed as Gaussian. So that's the typical, the simplest modeling scenario that you may think. So you have some experimental, some data here, where you have, for example, here some value which may represent somehow the position of the mean in an histogram. Then you try to match it with some continuous distribution, and you try to put it into the model, and out of this you try to get some information on some quantity of interest, where you have, for example, here the expectation of your profile and some confidence bound that give you the possible variation of the solution with that essentially random input. So the source of uncertainties may be very different. They may range from what are called usually epistemic uncertainties, so which may due to incomplete knowledge of the system, which means basically which is something that in principle we can get rid of just by improving the measurement or improving the technology, which essentially is at the basis of our measurement device, but for some reason, because maybe if it is too expensive or unfeasible, then you are not including it in your model, but in principle you could have. Or you have other uncertainties which cannot be essentially reduced through improvements in measurements, something that you cannot predict and there's no way that you can measure, which are referred typically as aleatoric uncertainties. So actually, from a numerical viewpoint, what is quite interesting is that, or from the point of view what is called uncertainty quantification, the real origin of the source of uncertainty doesn't really play a major role in the selection of the numerical technique, okay? So we select our numerical technique, as you will see, accordingly to other more general principles, or let's say properties of essentially the random variable which are used to model essentially the presence of uncertainties. Here, there's just a short list of typical uncertainties that we have, for example, if we use as a mathematical model a partial differential equation, or in general a differential problem. The classical uncertainty is in the initial data, or in the boundary condition, and these are classical uncertainties which comes from, let's say, additional terms that are essentially embedded in your partial differential model, which remains fully deterministic. But you can also have uncertainty in the modeling parameters, like the microscopic interaction term, external forces, viscosity coefficient, and this is going to make your partial differential equation essentially uncertain, okay? It contains naturally uncertainties. Again, there's not much difference in the way we are going to deal with them. So uncertainty quantification is somehow the task to determine information about the uncertainty in the outputs of our system, given information about the uncertainty in the inputs. Of course, if the system is a partial differential equation, then this setting is shortly summarized here. We have some statistics about the uncertain inputs. You include this in your partial differential model, then you get uncertain solution of the partial differential system. And the idea is that through some post-processing of the solution of your partial differential equation, you get some statistics about your uncertain output of interest. So the output of interest are the particular quantity that you will focus on. These are quantity that typically depends on the solution of your partial differential equation, and for which we want to know some statistical information. So now let's go to the general modeling. What we typically do is we assume that this uncertainty can be modeled as a set of random parameters. So typically I have a finite set of random numbers, Z1, Zd, where dz is the dimension of our random space, that we collect in a vector, our random vector Z, which lives in the multidimensional random space. Just to be more precise, you have to think to this random vector. For example, you can think that the first entry, for example, is due to the uncertainty in the initial data, or the first true entry eventually, or three. But the first group of entries refers to some kind of uncertainty. The second group refers, for example, to uncertainty in the boundary condition. The third group to another kind of uncertainty. So you have many sources. You just store them all. You summarize them all in a vector. Well, actually, just to try to simplify things, as you will see later on, I will just assume to have only one single source of uncertainty, but that's just for simplification reason, at least in some cases. So now, for example, if we just to fix the idea, we want to write down a model which has been widely introduced by Giuseppe in the previous lecture. So, for example, a Fokker-Planck equation. A general Fokker-Planck equation with random inputs will read somehow as follows. So you have your solution now, which depends on an additional variable, so our random vector, okay? And we can have, as you see, part of the uncertainty can be due to the initial data, then part of the uncertainty can be due to the coefficient which appears in the advection term, part of the uncertainty to the coefficient which appears in the diffusion term, and then of course your solution itself is going to depend on these parameters, okay? So this is just to fix the idea on what we mean for a partial differential equation with random inputs. Of course, we could have had the hero's boundary condition, for example. Now, a realization of a solution of the partial differential equation is a solution which has been obtained for a given set of random parameters. Okay, we are not dealing with a stochastic differential equation here, because what you have is really a deterministic equation which depends on random inputs. Okay, so once you fix the random inputs, if you make a choice, then all the problem is fully deterministic. Okay, so for a given set of random parameters, a solution of the PDE is usually referred to as a realization. What we want, of course, we are not interested in obtaining a realization of the solution of the PDE, otherwise there would have been nothing to do, everything would be deterministic. What we are interested in is we want to obtain statistical information out of this partial differential equation. So typically we are interested in expected values, for example, of the solution of some other quantity, or variances, or standard deviation, covariances, higher statistical moments. It depends on the particular problem you have. So let's try to see a little bit how the thing works. So essentially, the way we typically determine our quantity of interest is the following. First, from the solution of our partial differential equation, we define some output of interest f of u. Okay, this is some quantity which can be, depends, we will see example later on, it can be even the norm of the solution or whatever thing, okay, which has a functional dependence with respect to the physical variable, actually, with respect to the solution. So once we decided that we want information about this quantity of interest, then we choose what statistical information about this quantity is desired, and we define a statistical function psi of the quantity of interest, which has essentially the estimate of our quantity of interest as the expectation of psi of f of u, which actually is a multidimensional integral over the probability space. So, examples.
Sorry, is there a principal difference between the psi and the f?
What do you mean by difference?
No, why not just talk about psi combined with f?
Because f is typically something which works in the phase space of the solution, whereas psi works on the random space. So that's a good idea to keep them separated. But if you see now the example, it's pretty clear. So for example, f of u, you take your L1 norm of your solution, okay? Then of course f of u is going to depend on the random parameter, right? And then you can take, for example, as function psi, the identity. So this is going to give you as quantity of interest the expectation of the L1 norm of the solution. Okay? So another example, you take f of u equal u, so it's the identity, and now psi of u of w is w minus the expectation to the square, and then what you get as quantity of interest is the variance of your solution. Okay? So this concept can be generalized because there's no reason why psi has to be a function of a single argument. If you imagine that psi is a function of two arguments, and then you apply the above estimator to two solutions, f of u1 and f of u2, where u1 and u2 are two different solutions of your problem, then the above estimator gives you the covariance between the two quantity f of u1 and f of u2. Okay, so these are all examples of quantities we may be interested in. So now let's discuss a little bit the general computational aspect of uncertainty quantification for partial differential equation. The first thing is that the computational cost associated with uncertainty quantification increases with the number of parameters that we use to model the uncertainty. This is completely clear, no? Because we are adding one dimension. Well, let's say we're adding one variable which lives in general in a multidimensional space. So the functional dependence of your solution increases its dimensionality. And this typically originates the so-called curse of dimensionality, which is a general problem of uncertainty quantification, but it is particularly relevant, as we will see, for kinetic equation. There are two main general strategies that we can use to alleviate this problem. So, the first one, because the point is the following essentially, if we just move back, for example, to this setting, imagine that you have one realization of your solution here, okay? And then you have a set of random parameters. Of course, in order to accumulate statistics, typically what you should do is to solve many times this Fokker-Planck equation and then to try out of all this solution to get some way to accumulate statistics, okay? And then you may imagine that this model, this is a price that we don't want to pay because typically maybe the model we're interested in is very expensive. So how we can reduce this cost? Well, one first strategy is essentially based on simplifying this model, trying to find a simpler model which gives us, in any case, some interesting information concerning the statistics, okay? Because we are interested just in average quantity typically with respect to the random parameter of the solution. So there may be that we can simplify things and find some model which is essentially simpler. That's it. And this is usually, the idea is that you can try to combine relatively few solutions of your partial differential equation and replace the partial differential equation with a surrogate model, which usually is referred to as low fidelity, which is much cheaper to solve. Okay, so we can accumulate statistics essentially for free with that model. And then we can try in this way to get some information at a reduced cost. This is one strategy. And the other strategy is if we have smooth solution, then we can try to design method which permits an accurate evaluation of the expectation for our quantity of interest, which, let me remember that this is a multidimensional integral, okay? So we can think about being as efficient as possible in order to compute this integral with some kind of quadrature rule, okay? But then of course we need some smoothness because otherwise there's no way, okay? So if we have some smoothness, then we can imagine we are smart enough to develop something which uses just few quadrature points. And this typically, the strategy is based on the use of stochastic orthogonal polynomials. Okay, these are essentially the two main words, the two main approaches that are typically used in uncertainty quantification, with many small declinations of these notions, but essentially these are the two building blocks. Let me also say that we are tacitly assuming that we know the probability distribution of the PDF, okay? the probability distribution of the random variable. This typically in practice it's not known, and this originates a completely different problem because then we have essentially to solve a stochastic inverse problem, which basically is by studying the output, the outcome of the model, we can try to reconstruct the effective probability distribution of the input parameters. Okay, this is a very relevant and important topic, but I will not discuss at all about this. This is usually called the inverse uncertainty problem, and we just work in the forward direction. Okay. So, in a nutshell, the main techniques which we can adopt to deal with this problem. Of course, the simplest approach is based on Monte Carlo sampling, where the idea is that you sample your input. For each sample of your input, you solve a deterministic problem, and then you just use the results by combining them in order to compute the expectation. So essentially, the integral that you have seen before is replaced by the statistical mean. Okay? So this is very general, it's easy to realize, but it has low convergence and typically present fluctuation in the solution statistics. Multi-fidelity, multi-level methods are a way to accelerate sampling method by using various surrogate models. So basically the idea is the following. Typically we know that Monte Carlo has a slow convergence, and then we try to see if we have simplified model that for which we pay a lower price to compute the statistics, and try to use that kind of information in order to reduce essentially the variance of the expected the expectation of the quantity of interest. We will discuss this essentially. This point here is what we're going to discuss in the lecture of tomorrow. And this too essentially refers to the strategy 1 in the approach to UQ. So both things are based essentially on sampling. Then if we have some information on the smoothness of the solution, and in particular on the explicit expression of the probability density function of the random input, then we may imagine to express solution as orthogonal polynomials of the random inputs exactly in a classical Galerkin setting, which in this case is called Stochastic Galerkin, because the variable we are playing with is not a deterministic quantity. And we have the usual things that we get for spectral methods, namely we can prove spectral convergence for smooth solution in the random space. Of course, we require in this case smoothness and knowledge of the PDF. There are many other methods. Again, I will just try to give you ideas in some directions. So a classical method for people that works in kinetic theory would be to use a moment method approach. So just derive essentially an equation for the quantity of interest. That would be the reason, the idea. But of course, we all know that this typically brings out the closure problem. So it's a kind of approach, however, which may be used, especially for linear problem. It applies without any difficulties often, but unfortunately, in all the situation we are typically interested in, the problem we are dealing with are non-linear. Or stochastic collocation method, which somehow try to take the best of both worlds, in the sense that they avoid the Galerkin projection, and they're using as particular sampling points the zeros of the orthogonal polynomials of the random inputs. But there are also other ways to realize this stochastic collocation method. So here are just some general references on this topic. The first one is a classical reference on uncertainty quantification, which somehow covers all the various fields. Is a text which is rather introductory and can be used to learn uncertainty quantification essentially from zeros. And the other two tests refers essentially, the second one to the use of uncertainty quantification typically in fluid dynamic, and this more recent one that I edited together with Shijin, that it contains essentially a collection of state-of-the-art contribution up to 2017 in the specific field of kinetic and hyperbolic equation. Here are also some basic, let's say, reference. They have all been published on Acta Numerica. So essentially, they are large surveys. In this way, they're going to include a lot of reference, a lot of material. It's already written down in a way typically that can be used for a course or to learn things. So this is the classical reference by Raskaflish on Monte Carlo and quasi-Monte Carlo methods. Then there is this one by Gunzburger, Webster, and Tank on stochastic finite element method for PDE, where essentially here the focus is more, let's say, on elliptic and parabolic problems, but there are several contact points with the hyperbolic and kinetic equation, and the reference by Giles on the idea of using multi-level Monte Carlo method in order to improve the statistics of Monte Carlo methods. So, what I will do right now is to describe to you the way the Monte Carlo method works, the basic Monte Carlo method works, why it works, and try to hopefully to give you the right message where we should act in order to improve it. And then I will do the same thing for stochastic Galerkin methods in their basic application, and in order to try to pass you the message of the way it works and what we should do in principle in order to try to improve it. So, Monte Carlo method is of course one of the favorite methods for uncertainty quantification because it's really extremely simple. It doesn't depend on the dimension of the random space. So in the formulation here, I'm not assuming anything. You can imagine that the random space is multi-dimensional. Essentially, the method doesn't see it. And just in order to focus in a specific setting, not to leave things to let's say, esoteric, I'm going to just focus on the situation where my partial differential equation has uncertainty only in the initial data. Okay? So I have a deterministic PDE with an uncertain initial data. That's the setting I'm going to describe things. Okay? But it's the same even if you have other source of uncertainty. There will be essentially no modification except in the way the method really works in detail. Okay? So in this case, the method is based essentially on 3 steps if you do a Monte Carlo method. First, you sample m independent, identically distributed initial data. Okay? This sampling can be done in different ways according to the kind of information you have. For example, if for some reason you know the probability distribution, then you can realize it artificially, for example, an experiment that we realize on the computer, but this can be just a set of initial data which comes from experiments. Okay? So we don't need to know the specific distribution at this level in general of the random variable. This is a very important thing. And then, of course, what we typically do, we are solving a PDE, you have to approximate these things on a grid and to get your family of initial data over the grid. Okay? This is step 0. Step 1. Now, the step 1 is really the second reason why Monte Carlo method are a favorite way to solve uncertainty quantification, because at the step 2, you just take your old deterministic solver that you have done for a completely different problem, and then you just feed for each initial data, you give the initial data to your deterministic solver, you let it run, compute the solution, and take out the statistic, then initial data number 2, and then you go on, okay? And think already that all these things can be done in parallel, because there is no relationship between the various solutions, okay? So you can do it in a highly parallelized situation. So then what you get is a set of deterministic solution, but each one which refers to a different initial data. Okay? So these things here, from a probabilistic viewpoint, are going to represent our samples of the solution of our partial differential equation at time Tn. So the third step, we just estimate the desired statistical information of the quantity of interest, which is this one in general, just by the statistical mean of it. Okay? We just take, essentially, we take the average of the quantities of our quantity of interest. So it's extremely simple. As you see, there's no particular, let's say, modification of the method according to the fact that the random space is one-dimensional, two-dimensional, three-dimensional, or general, of a general dimension. The structure is the same. So let's see how the method works, and let's try to discuss a little bit the error in relation to the computational cost. Now, in order to fix the idea and to make Christian happy, I'm going to just take fu equal u and psi equal w, so the quantity of interest is the expectation of the solution. Okay, so very simple. Of course, nothing essentially changes if the argument can be applied, even in a slightly less direct way. So the starting point of the reason why Monte Carlo method converges is essentially due to the central limit theorem. So we know that we have mean square convergence, and so essentially then if we take the expectation of the difference, the square of the difference between the statistical estimate and the real estimate, and we take everything to the square, so which is usually referred to as the root mean square error, then actually in the general scenario this is really equal, and this constant is equal to 1. But let me put it in this form, because typically for PDEs you may have other sources of error, and so typically that's the kind of inequality we are gonna use. So you have this inequality which is sharp, which tells you that the expectation of this quantity, essentially the case has the square root of the number of samples, which is the classical Monte Carlo estimate. Okay. Another way to see this is that if you consider what you have here, if you write it in a, remember that the expectation is the integral of the function against p of z dz. So if you introduce the weighted L2 space with respect to the probability density function p, and we typically in this field typically this is simply denoted by L2 without any additional p on the bottom, because it's completely clear that we are using this kind of L2 space in the random space. Then this is convergence in the weighted essentially L2 norm. Okay, so of course one can be more precise in terms of probability by doing the usual story. You say I have omega, I put it in Borel algebra and blah 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 blah, but this is irrelevant for what you're saying. Okay, just formalism, which doesn't change at all the thing. So far so good. Now this is one source of error, is the statistical error. Then of course in step number 2, we are solving our partial differential equation by our old-fashioned deterministic solver, and we assume that for this deterministic solver we have some consistency estimate, okay, so that we are using something that works, which gives out some error with respect to delta x and up to some power p, so that we are using a method of order p in space. Now, we typically, if we want to write a general error estimate, you have to combine these two norms, and you have two ways to combine the two norms. So one way is essentially to take the expectation of your physical norm, so the LP, now this LP is in space, so it's with respect to x. So and this, so basically you take first the norm with respect to x, and then the norm with respect to z, and that's the way you typically write it down. Or the other way, you do first the expectation of your quantity, and then you take the norm with respect to the physical quantity, okay? Because you have two dependence. So these two norms, that's the way you denote the second one. These two norms are related by the Jensen inequality, so which means basically the norm 2 is less or equal than norm 1. Actually, for p equal 2, the two norms are the same. Okay? In L2, L2, these are two norms, of course, they are identical. The discussion by using norm 2 is slightly simpler, so that's the reason why I'm going to now consider norm 2 and p equal 1. So I'm taking L1 as a norm in x, and I'm first taking the expectation with respect to the probability space, and then on the top of that I'm using the L1 norm. Okay? So it's simpler because in this way I can apply just essentially probability arguments. So of course what we can do is the following. So this thing here is going to measure the difference between the expectation of the solution of time tn and the statistical estimate of the expectation of the solution approximated over the grid of size delta x, so that we have the two sources of error. Then it is natural to split the error in two parts. In the first case, we estimate just the statistical error, which is the difference between the expectation of the solution minus the expectation of the solution evaluated just by using a statistical mean over the samples. And basically what you're doing, I'm adding and subtracting here this quantity inside this, and then apply a triangle inequality. And then in this way, this is just a spatial error, because you see both of these are statistical estimate, but this is the statistical estimate over the true solution, and this is the statistical estimate over the solution of the grid. Okay? So now, in this way, I can bound this thing here, essentially, by, let's say, the classical result that I've shown you before due to the central limit theorem. So I1, the first error, is bounded by some constant, the norm of the standard deviation of u, the L1 norm of the standard deviation of u, m to the minus 1/2, because I'm applying essentially on the top of the inequality, I'm applying the L1 norm. Okay? And remember that the standard deviation is going to depend on x, so now that's the reason why I have this norm on the top of that. The spatial error, you can bind it just by writing it in detail here, and then each one of these terms is essentially bounded by our consistency estimate, which gives us some constant ck delta x to the power p, and then you collect delta x to the power p, and then you define this to be c2, and that's the kind of estimate you get. Okay? The two natural things. So there's nothing surprising, basically. What we have shown is that the error is composed by two terms. A statistical part, which decays as the square root of the number of samples, and the deterministic part, which decays has the order of the discretization that we have used. So now where's the point? Well, the point is that you typically try to equilibrate these two sources of error. Okay? That's what you want to do. So if you want to equilibrate the two, it means that your m, so the number of samples that you need, remember the number of samples means the number of time you have to solve your PDE, basically. Okay? It has to be of the order of delta x to the power minus 2p. So basically, it tells you that if you imagine to have a general method of order p, and you change the grid from delta x to delta x over 2, so you refine the grid, what happens to the number of samples is that you have to multiply your number of samples by a factor 2 to the power 2p, okay? Which is a huge number, okay? Which means basically that if p is large, so ready for p equal 2, you need a lot of samples in order to get comparable error. Okay, this is the classical, of course. You have a method which converts like the square root, and another which converts like some power p. That's somehow the main drawback of Monte Carlo method. That's where we want to improve that, basically. So, but this is a classical, I would say. You can say that almost all works on Monte Carlo method in various fields, they are all essentially, the main aim is to accelerate the convergence of the Monte Carlo method. But nevertheless, it has many desirable qualities as we have seen. Now, a different approach is based on the use of stochastic orthogonal polynomials. How this works, I will describe you here quickly. The approach is fully deterministic in this case, even though behind there is the probability notion, but you will see it. So let's imagine that we have a one-dimensional random variable, okay, just to simplify things. So z lives in 1D. We have only one parameter. Now, the method is based on this, this idea. The idea is the following. We have, at the end of the day, to evaluate, when we compute the statistical estimate, an integral of a quantity against a weight. And this weight is this probability density function. So the idea is, why we don't construct a set of orthogonal polynomials that I denoted by phi m, which are of degree less or equal to m, which are also orthonormal with respect to our probability density function. Namely, they satisfy this identity here, okay? So they are orthonormal with respect to P of z. But you see that to this classical numerical analysis relation, now we can give a probabilistic formulation, because this is nothing else than the expectation of phi m times phi n. And this is equal to a Dirac delta. Okay, it's 1 if it's the m is equal to n, 0 elsewhere.
So Kronecker delta.
Kronecker delta, yeah, sure. So the one important thing is that this set of orthogonal polynomials are hierarchical, namely phi m has degree m, typically. Okay. Now the solution of your partial differential equation is represented exactly as you typically do in spectral methods by expanding by representing your solution in terms of the basis represented by your orthogonal polynomial, where each coefficient here is nothing else than, as we know, the integral of u against the polynomial phi m with respect to as usual the weighted scalar product with respect to the probability density function, which we can also write again in statistical terms like the expectation of u times phi m. So you see, this is except for the fact that z is not a deterministic variable, the structure is the same as with classical spectral method. But of course the situation is different formally because z lives in some probability space and so on. This stochastic Galerkin approximation in the field of random PDEs are typically referred to as generalized polynomial chaos. And the terminology comes from the fact that Wiener uses first this representation in the case of Gaussian distribution, so essentially white noise, and he uses the terminology polynomial chaos. And so, as a sort of tribute to Wiener, then the community adopted this polynomial chaos terminology. But from the viewpoint of, let's say, approximation, these are essentially stochastic orthogonal polynomial-based expansion. Okay, so now, for the quantity of interest, of course, then we have the usual representation that you have seen before. We need to evaluate this, and we can imagine that this is evaluated by using the same quadrature, which typically is Gaussian because of the use of orthogonal polynomial that have been used to compute this coefficient here that needs to be computed at the very beginning, typically, of the simulation. Then the rest of the game plays just using the coefficient in in the expansion, as we will see. So for the quantity of interest, in some cases we don't need to go through this particular computation. For example, the expectation can be recovered immediately. It is just essentially, let's say, the coefficient of order 0, and for the variance we get similarly just by applying the orthonormal property of the polynomial basis, that this can be computed as by using this formula, which is very close to the classical formula for the computation of the variance. So let's discuss a little bit error versus cost even here. So if you take a general partial differential equation that we wrote now in this form here, okay? We have some time derivative of u, and here we have some differential operators. So the stochastic Galerkin method basically corresponds to the following. You just replace u with um, and then you project everything back to the, because this operator typically it acts as a combination of solution of u, so the result may essentially gives you something which is no more in the original space of orthogonal polynomials. So it is usually done in Galerkin method. So there is replacement and projection. So you replace u by um, and then you project everything just by taking the expectation against the polynomial of order h. So that's this part here. It's linear, so it's no problem. This gives you the time derivative of the coefficient of order h. And this is equal to the expectation of the quantity you have here. Now, this point here is the delicate part of the story. If you have a linear PDE, so which I denote by L, then, of course, the expectation enters into the operator, and then you simply get a set of m plus 1 differential problem which resemble in all your original problem. Okay. The problem comes if you have a nonlinear problem. For example, consider a bilinear partial differential equation, as it is quite common in kinetic equation. Then we denote j as q of u and u, and in this case, by just taking the expectation and by applying the bilinearity, we get this representation here. And you see now that here you have a double sum on m and n, which goes from 0 to n. So you have an additional quadratic cost, which is of the order of m to the square. Remember that here I'm playing the game in one dimension. Okay? So we will see then what happens if we take a multiple dimension. So for nonlinear problems, we pay a price. So this the price we are paying, as it is typical of spectral method. Imagine you apply classical spectral method to the Burger's equation. If someone has done this during some lecture, that's exactly the same. Same thing, same result, no different. And we all know that you have to pay a price, and the reward typically is the accuracy. Okay, so here we are paying a price. For linear problem, we are not paying the price. And one additional problem, which again is typical of spectral method or orthogonal polynomial approximation, is the loss of physical properties. So if our partial differential equation has some structural properties like positivity of the solution or other invariant, and unfortunately this is the case of kinetic equation, these properties are typically lost by the projection. Of course, it's the usual thing. We may hope that even if we lose them, we are losing them in a very small way because of the high accuracy of the method. So let's discuss a bit error versus cost. The main interest in stochastic Galerkin method and in spectral method in general is due to their convergence properties, which are usually referred to as spectral convergence. So in this case, we are talking about smooth solution in the random space, okay, not in the physical space. So the smoothness has to be in the space of parameters. So now let's imagine that our solution u lives in hr of omega, which is the weighted Sobolev space in weighted as before because we are taking integrals against the probability density function, so it's the weighted Sobolev space of index R. So we have the following estimate for the L2 omega error, so the root mean square error. For the root mean square error, the kind of estimate we have now is that this is less or equal than some constant, then you have the norm of the solution in your Sobolev space divided to m to the power r, and typically this, as you see, this holds for m large enough in general, so m has to be larger than something, and then you have exactly this kind of estimate. So you see that the highest is the smoothness, and the strongest is the fastest is the convergence. So for analytic function, you have function which are infinitely smooth. You have the famous spectral convergence, which essentially corresponds to exponential convergence in the space of parameters. So that's one of the main reasons why there is interest in stochastic Galerkin method. So now, if you are in this setting, then you have to equilibrate a narrow relation of this type now, if you have a method of order P in the physical space, with R, however, which in general is much larger than P. So you have to use a very small amount of M in order to balance the error in the method. That's the core point. You may pay a price, but if the solution is smooth, and if you know the PDE, very few number of samples of modes, in this case, are enough in order to get an accurate solution. One of the problems here is that once you move to multidimensional random spaces, then there are some limitations in the application of these techniques. Well, if we assume that we use the same degree m in each dimension, and we have also to assume, in fact, that our probability density function is essentially that we have an independent variable, so that it's going to factorize, right, with respect to each argument, because otherwise the method it essentially cannot be applied. Then the problem is that the number of degrees of freedom grows tremendously in the polynomial space, and that's the total number of degrees of freedom if the dimension for a general dimension of the random space dz. So just to give you an example, if we just use 5 coefficients in each dimension of a 3-dimensional random space, it gives you that k is equal to 320. So for a nonlinear problem, this cost has to be squared. Okay? So this, of course, it may be a high price to pay in order to have super convergence. That's one of the reasons why, in most cases, so they suffer a lot this course of dimensionality, and so then very special techniques you have to go in order to go to the multidimensional setting. Okay, so I think I've essentially exhausted my time, right? But I started 5 minutes late, so I can work a little bit more. So now, after this introduction, my main topic of my lecture will be on kinetic equation. So, of course, the application of the previous strategies of Monte Carlo and generalized polynomial chaos to kinetic equation can be done exactly following the approach that I just illustrated before, okay? Of the basic method. These two are then, let's say, the pillars that I'm going to use to develop, let's say, more efficient or more interesting or method which have some additional properties. So, in the case of kinetic equation, the general model I'm going to focus on has this structure here. So, it's, again, my distribution function f now depends on an additional parameter z, which is a random vector, which lives in some multidimensional space, eventually. And as you see, one thing that you should immediately catch is the fact that if it's already a pain from a numerical viewpoint to deal with f, which depends on x, d, and t, now you have on the top of that, you have also z. Okay? So this thing here in general is a function which lives in a highly dimensional space. So classical examples are given by the Boltzmann equation where the additional uncertainties can be contained, for example, in the collision kernel, or by Vlasov-Fokker-Planck type models where the operator P, for example, is a non-local operator of this type, and again you can have additional uncertainties here, but you can have also uncertainties in the local relevance of diffusion, just to give you examples. Okay? So, in general, what are the typical facts of kinetic equation that we're going to try to use? Well, the fact that you have a random input is not going to change the classical result of kinetic theory. Namely, for example, here I'm just thinking to a general situation, okay? Then in order to make things a little bit more concrete, I'm going to think about the case of rarefied gas dynamics, or in general to a case where the collision operator, the interaction operator you have on the right hand side is going to be conservative with respect to mass, momentum, and energy. Okay? So the first thing you have is the conservation of mass, momentum, and energy. So namely that this structural property of the collision operator, where you integrate it against 1v and v squared, and the entropy inequality. We know that the quality holds only if F is a local Maxwellian equilibrium, but now as you see, the local Maxwellian equilibrium is going to also depend on your random parameter, because it's determined by the density, mean velocity, and temperature of the gas, which are just moment of your solution. Since your solution is going to depend on Z, then rho, U, and T are all going to depend on Z, X, and T. Okay?
So your Z was inside the collision kernel only?
No, at this level it doesn't matter. The Z is just just part of the solution. So you have uncertainty in the initial data.
But you plug it in only on the...
No. You have to make, if it is inside just the collision kernel, then the equilibrium state is independent is independent on the randomness. So it's an easier.
It's everywhere.
Yeah. The case where the collision kernel depends on Z in some sense is the simplest case in this case in the field of uncertainty. It's really typically we are always assuming to have uncertainty in the initial data, okay, which is the most common setting. But it's your remark is correct. In the case we have only uncertainty in the collisional cross section, then the equilibrium of course is not going to depend on the uncertainty anymore. Hydrodynamic limit, and then I'm going to stop here. We do the usual thing. So we take moments, the system is not closed, and we know that the simple way to find an approximate closure, for example, is to take F equal to M, and then we get the compressible Euler equation with random inputs, where again we have this dependence from Z. So all this is rather classical, but with the main difference that now the models, they all depend on the random, they all depend on the random inputs. I think I'm stopping here. Thank you.
Are there any questions?
Just kind of a comment question. If for the typical data you are interested in as output of kinetic models, you might kind of consider V as part of the Z also. And very often you are interested in macroscopic information in the end.
Yes. Well, more than you are interested in getting statistical information about the moments, which is not exactly the same as taking the V together with the Z.
Yeah, but you are interested in macroscopic density, temperature, and so on, right? So
yes.
It is like statistical information where V is part of the
stochastic. The main difference is that in the case of V, you already have, let's say, all the statistics. So you just integrate your quantity and you get your representation, which is free of noise, free of everything, unless you are using some Monte Carlo simulation. Okay. In in the random space, typically you have to deal with a limited amount of data and things like that.
What about randomness in the boundary?
Yeah,
Quantification.
yeah.
It's a physical relevant problem.
Yeah, absolutely. I'm going to show you an example about that. As I was saying at the beginning, independently of the source of randomness, the kind of treatment you do of the equation is essentially the same. Because the core point is to assume that your solution F depends on the randomness. Then, of course, this dependence may be originated from the boundary, okay? So the model may be fully deterministic, but the boundary has some uncertainty, okay? Or, which is a classical problem, which is very interesting, especially in kinetic theory. Or it can be determined, for example, even the fact that you give some Riemann problem initially, where the shop location is uncertain. This is another very interesting problem, especially for small number when you're close to a compressible Euler regime, so where the shop is propagated. There are many interesting then properties. Up to now, I'm not, let's say, I will give you examples, numerical examples in all this direction.
You assumed finitely many random variables. If you consider infinitely many, for example, with the Cohen-Löw expansion, can you still obtain the hydrodynamic limits in this case?
Well, in principle, I would say yes. It depends just on the formalism you use from the very beginning, because it's still the solution. It's a little bit like writing z now as a continuous variable. It's a little bit like switching in classical kinetic theory from a discrete velocity model to a model with a continuous velocity. And then I don't see why it shouldn't work. I never did it, but I would say yes.
Okay.
In a similar direction, when you, for instance, you put your Z into the collision cross-section, but that means basically for different realizations you consider different types of particles, but it's always all the particles the same type, right? You take one realization, you change in a way the type of particle, but then it's all the particles have the same type, and what you might want in reality is kind of a mixture of particles, right? Then it gets much more complicated.
Yeah, well, then it depends, because if you stay, let's say, at the level of stochastic Galerkin method, you really don't see any more the physics. Okay, so you just approximate your PDE with some degree of accuracy. Okay, it's just a matter you model that variable z with some random parameter. You assume to have some distribution of that, and then you do all the things by forgetting about all the physics. If you stay at the Monte Carlo level, then I agree with you. It may be. I mean, there are two ways, in some sense, to realize it. In one way, you take many samples for each particle, and that would be very, very, very expensive. A more natural way would be to imagine that this parameter, the z, essentially plays the same rule as space and velocity. So basically, you take one particle, and each particle has a characteristic as its velocity position and its randomness. And then you mix up everything.
Okay, there are no other questions, so we thank the speaker again.